Alright, this is Doppler effect, and this relation describes the effective frequency we hear whether the observer, aka us moving, or the source moving. And in kinematics, when we see two velocities, because the motion is relative, we usually just combine these two velocities, or combine any number of velocities together to form like one relative velocity to simplify the whole thing. But it turns out in Doppler effect we cannot do that. And I've been wondering about this until I sort of derive Doppler effect step by step and really understand the physical meaning of these additional terms to it. So yeah, this video is dedicated to answering the question, why can we not combine V observer and V source together? So let's get into the cases. Case 1. Well, this is, I sort of visualize the sound wave as packets on the conveyor belt, and these packets are donuts in my case. The conveyor belt is traveling at 343 meters per second, and our observer is riding an electric scooter against the direction of the sound of the conveyor belt at 10 meters per second. We can find the frequency using the equation shown here, f equals to v over lambda. But of course, since conditions are different, things are moving, we'll be having f prime equals to v prime over lambda prime. And now we want to figure out v prime and lambda prime. Lambda prime refers to the distance. Well, it's the wavelength, and in the donut conveyor belt case, it's simply the distance between two donuts. And it's pretty obvious to see that the distance between donuts will not magically change because someone is riding a scooter on the side. So lambda prime equals to lambda. But v prime, this is now the relative velocity between the speed of sound and the speed of the observer, because, well, they're traveling against each other, and their velocities should add up to represent the whole velocity. So we got these equations. We got the relationship, and we simply plug in lambda prime into the denominator and v prime into the numerator, giving us f prime equals to v plus v observer over lambda. So this conforms with the form of the Doppler effect, that v observer goes on top of the fraction. So that's the first case, with observer moving and source not moving. In the second case, we look at a standing still observer and a moving source. So this is, say, the end of the donut production line, and it's dropping donuts onto the conveyor belt every t seconds. This value is not dependent upon the conveyor belt at all, because this is somehow the production capacity of the donut factory. And so this is also the information that we can use to calculate the distance between the donuts, because every time a new donut drops onto the conveyor belt will travel by a fixed distance, represented by lambda. Lambda equals to v times t. T being the time we produce donuts. And with our depositor moving in the same direction as the conveyor belt, we should expect the distance between each donut gets smaller, because to the depositor, to the donut depositor, the conveyor belt is not traveling as fast as it used to be. And so the new lambda prime will look like v minus v source times the same time, times the same t. And we plug in lambda prime into the new equation finding f prime, we got f prime equals to v over v minus v source times a fixed time. So what is this equation telling us? The equation, unlike the previous case, where the observer riding a scooter has nothing to do with the conveyor belt setup, aka the wave, observer is not affecting the wave at all. But when the source is moving, we're actually creating different waves because the distance between each wavefronts, the wavelength, the lambda prime, is now shrinking down a little bit due to our depositor or our source moving. So if you can imagine this, we have a magical camera that can take pictures of the sound. When we take pictures of the moving observer sound, the sound will look just like how it should look like coming out of the source. But when the source is moving, we're taking a picture of a different sound, nothing like what the source intends it to be, and nothing like what we can see in the previous case. So to me, changing the source velocity is almost a more fundamental modification to the wave, to the Doppler effect that we're seeing. And because of this reason, the source velocity is not counted into our normal kinematics velocity due to its special effects. Okay, so we've answered the question, but we've almost derived how the full Doppler effect is, so we might as well just do that. This is the more general case. We have our donut depositor, the source, moving at some speed, and our observer also moving at some speed. And I just copy-paste the lambda due to moving source and the v due to moving observer from the previous case down here. And we do the substitution. We got f prime equals to v double prime over lambda double prime equals to v plus v observer over v minus v source times t. And what's that t there? T almost have its twin brother represented just in f, because f times t is, this is how we define frequency actually. Yeah, this is how we define frequency. So f times t equals to 1, and we can replace t with 1 over f. We make the substitution into f prime. We got f prime equals to v plus v observer over v minus v source times 1 over f, and we flip it onto the denominator, taking the 1 over thing off. We got f times v plus v observer over v minus v source. This is almost the same as the equation that we started the video with, except for the plus and minus signs. And that's because I chose very specific directions for the observer and for the source. But in general, they can move left to right, whatever they want, and we will be having the same plus or minus choice to make in the most general case. So yeah, this is pretty much Doppler effect, and we've also derived, we've also made the derivation of how it came about. So hopefully this video clears up some of the more obscure details from the somewhat mysterious and, well, they're very symmetric. And it's tempting to think of the effect of V observer and V source as the same thing. But if you look into the more obscure details, of course, as I've shown you, they are pretty different. So yeah, that's the end of the video. Thanks for listening.